The next properties of Sturm-Liouville problem set. So the next property, okay, is the eigenvalues. Sorry, eigenvectors, which is correspond to each eigenvalues. So for lambda 1, lambda 2, lambda 3 until lambda n, you will have the eigenvectors y1, y2, y3 until yn. It will form an orthogonal basis set on the subdomain or subspace of x belong to A to B, which satisfy the boundary conditions. And what is orthogonal? Here, just briefly saying what is orthogonal. The inner product of yn, ym will be equals to 0 if n is now equals to m. If n is equals to m, that means you have yn, right? Then that inner product will be yn squared. So that is the orthogonal properties, and we will make an proof later in the class how we can prove that orthogonal properties here for the eigenvectors. Okay. But here we will just use the conclusion that the eigenvector will form this orthogonal basis set on the subdomain of your interested, which is between your boundary conditions and A to B. Okay. The first properties, the last property, if any smooth function you can say fx, any smooth function fx is in the subdomain range, space range, where your x is in between A to B, then this f function. So this f function can be any function. It can be 1, it can be 2, this kind of constant, or it can be some polynomials, or it can be, any functions in between this A to B. And this can be written uniquely as a linear combination of the eigenvectors or eigenfunctions. That is, you have fx equals to the sum from n equals to 1 to infinity cn yn x, where your cn will be equals to the inner product of f yn divided by the inner product of yn. Okay, because if you have yn, there will be orthogonal will be 0. It doesn't make any sense. So the constant will be equals to the inner product of f yn over yn, and this is kind of like a normalized term because you have the denominator, which is yn. And we will show both the MATLAB programming and show by handwriting how this fx can be written uniquely as a linear combination of the eigenfunctions. Okay, so the next part, what we will do, we will use examples to elucidate the SL problem or SL properties. The goal here, the goal is first we want to find eigenvalues first. So as a SL problem, first you need to find the eigenvalues. Then after you find the eigenvalues, what is the corresponding eigenvectors, right? So find eigenvectors. Then we are trying to find a linear combination of the eigenfunctions to represent your fx, where your fx is a continuous. So here is very important. This is a continuous functions, continuous function that satisfy your boundary conditions. Okay. So we introduce the properties. First, the SL problem has infinitely eigenvalues. Then correspondingly, each eigenvalue will have a unique eigenvectors. So it will have infinitely eigenvectors. Then you can form a basis set using those eigenvectors, and those eigenvectors has the problem properties which is orthogonal. Then you can use this eigenvectors, linear combination of these eigenvectors to represent any smooth functions in between your boundary condition A to B. And if your smooth function is satisfied for the boundary conditions, then you can represent uniquely with a linear combination. And the constant is basically getting the inner product of your own interstate fx yn over yn, which is a normalized part. We will show examples for the SL problem, and we are trying to find, okay, first, what is the eigenvalues? What is the eigenvectors? Then you are giving a fx function, which is has to be a smooth function, satisfy the boundary conditions, and that can be uniquely represented by your eigenvectors you got from the SL problem, okay?